All right, so how do we handle situations where we have mixtures of gases in a container? And that uses the concept of partial pressure. So partial pressure is that's a pressure due to any one individual component, any one individual gas in a mixture of gases. And it's very simple. The total pressure of the container is just equal to the sum of all the individual components. So I have written here P total equals PA plus PB plus PZ, et cetera. And the pressure of any one of those gases is equal to the mole fraction, okay, times the total pressure of the container. So this X, or it's actually technically chi, Greek letter, chi stands for mole fraction. So if you have 50% on a molar basis, so you have 1 mole of hydrogen, 1 mole of nitrogen, and the total pressure is 1 atmosphere, let's say. Well, the mole fraction of both of those gases is 50%. And so 50% of the total pressure, in that case, would be 0.5 atmospheres. 0.5 atmospheres of pressure of one gas, 0.5 atmospheres pressure of other gas. Total pressure would be 1 atmosphere. And so here it's using kind of air as an example, which is mostly oxygen and nitrogen, looking at the total pressure, sum of nitrogen, sum due to oxygen. Those are the individual partial pressures. Together, they equal just the sum of those partial pressures to get the total pressure. All right, so here's a very simple question. If the air pressure is 1 atmosphere and nitrogen is 78% air, what is the partial pressure due to nitrogen? So we're going to use the formula that we just went over, that partial pressure of any gas, in this case we're asked about nitrogen, is equal to the mole fraction chi of that gas times the total pressure. And now it's given us in percentages, and this is a volume percent we're assuming, okay? And so if it's a volume percent, well, we know from the ideal gas law that volume is linearly related to number of moles. So this is the same thing as saying that the mole fraction is 78%. And so all we're going to do is P nitrogen equals 0.78, putting that percentage into decimal form. And the total pressure was given to us of the air was 1 atmosphere. And so the pressure of partial pressure of nitrogen in air is 0.78 atmospheres in that air. Okay, and you do a similar method for all these other components. Let's do a much harder problem. And so this one is asking us what happens if we drop calcium into water to form hydrogen gas at 21 degrees C. We're going to use some sort of apparatus like this. Here I'm showing zinc and hydrochloric acid to make hydrogen, but this problem is calcium and water making hydrogen. The hydrogen is going to form out of this reactor that's hooked up to a tube that goes underneath a beaker that's filled with water. What's going to happen is the hydrogen is going to form above this because it's lighter than water, and it's going to push the water down as it forms into this trough, okay? And so what's going to happen up here is we're going to have a mixture of hydrogen, mostly hydrogen, but also some water vapor. And the amount of water vapor there is going to be due to whatever the vapor pressure is, the pressure of hydrogen. And we're given the vapor pressure of water here. It's 18.7 millimeters of mercury. And we are told that the total pressure captured in the test tube is 748 millimeters of mercury. What is the pressure of the hydrogen? All right, so well, here what are we going to do? All we're going to do is use the fact that the total pressure is equal to the sum of the partial pressures. And the two pressures here that we care about are hydrogen, those are the two gases in this space, and water. And so we're given the total pressure. We want pressure of hydrogen. So pressure of hydrogen, if we just solve for this, is P total minus P water, which is equal to 748 millimeters of mercury minus 18.7 millimeters of mercury. And if we subtract that out, we get 729.3, or rounding to the nearest ones place, 729 millimeters of mercury. We can put 0.3 if we want. All right, now let's do this second part of the problem. If the volume is 51.2 milliliters, so the volume of this headspace here where we're capturing the gases, how many moles of hydrogen are produced? Okay, so here we have to use PV equals nRT, and we know the temperature. We know R is always the ideal gas constant. We don't know N, that's what we're trying to solve for. We know V of the total space, and we actually know P, okay? And so we have to be careful. What P do we use? Well, we want to use P hydrogen. I mean, we're talking about moles of hydrogen here. So let's just write that out. So the volume of hydrogen, let's solve for the moles of hydrogen. That's what we want. The moles of hydrogen, we know the volume. The moles of hydrogen is equal to the volume of hydrogen. What's the volume of the hydrogen? It's with water, but we don't actually care about that. As long as we use the pressure of hydrogen, we'll be fine. So that's going to be the 51.2 milliliters. We're going to have to convert that to liters, just to use the normal units for our ideal gas constant. So we're going to have N equals PV over RT. Okay, so we have volume of hydrogen. I wrote it VP here, but VP and PV, same thing, over RT hydrogen. Okay, and so now we can solve this out. Our volume of hydrogen, I'm going to convert that quickly into liters. So I just divide by 1,000, 0.0512 liters, times the pressure of hydrogen. We're in millimeters of mercury, which is equal to torr. So very quickly, I have to convert that to atmospheres, because I know my ideal gas constant down here that I'm about to use has the units of atmospheres, and it's 0.08206 liters atmospheres moles Kelvin, right? And so I know that there's 760 millimeters of mercury for every 1 atmosphere. So I'm going to be some number slightly less than 1 atmosphere. Divide that out, you get 0.9842 atmospheres. So put that in for our pressure of hydrogen. Okay, and then lastly, our temperature. What's our temperature is 28 C. Well, I need to convert that into Kelvin. So I'm gonna have to add 273.15, get that into Kelvin. And now I'm ready to plug that all in. So do 21 plus 273.15 would be 294.15 times 0.08206. And so this bottom part becomes 24.138. And then our top portion of that is 0.0512 times 0.9842 is 0.0504. And if we divide that out, we got 0.002. We can add a 1. It should be a 1 with rounding moles hydrogen. And that would be our final answer. So that's a little bit of a trickier problem. Key thing here was we had to use pressure of hydrogen, not the total pressure. It's the partial pressure in the container of hydrogen that we care about. Now, if you used, in this case, a lot of these problems, if you use the total pressure instead, because the vapor pressure of water is so small, you get a pretty similar answer, okay? But it will change it a little bit. So that's something just to keep in mind. All right, let's do one more here. So this one is saying a 12.5 liter scuba diving tank is filled with a heliox mixture containing 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin. Use this mixture of helium and oxygen. It's actually a prevents you from getting the bends. And there's some physiological reasons for that that are pretty interesting, but not going to get that into now. So what is the total pressure of the tank? It says calculate the mole fraction and partial pressure of each component in the mixture. We're given the mass. We're given, this is just kind of a summary. We need what we need to find and what we have. We're given the mass of each of these, and we're given the volume. And so we need to first calculate how are we going to calculate the total pressure, right? We're going to use P equals nRT, of course. And what do we have? Well, we always have R. We have V, volume's given to us. We don't have P, that's what we're trying to figure out. And we have T, 298K. So that's looking good. But we don't have N, total number of moles. So first thing we need to do is get our masses into moles. So we do that with the atomic weight. And so we look up on the periodic table. If you look up on the periodic table for helium, the atomic weight is about equal to 4.0 grams of helium for every 1 mole of helium. And so if we divide that out, we get 6.05 moles helium. And now let's do the same thing for oxygen. There's 4.32 grams of oxygen. And if we look up for oxygen, it's 16 grams per mole, but we have 2 oxygens, O2. So the molecular weight of oxygen is going to be 32 grams per mole. So 32 grams of oxygen for every 1 mole of oxygen. And if we divide that out, 4.32 divided by 32, we get 0.135 moles of oxygen. So our total number of moles is just 6.05 plus 0.135, which is equal to 6.185. Okay? And so now we can go in here and we can plug that total, because we're care about the total tank here, and it's all for P. Okay, so P is going to be equal to nRT over V, just dividing both sides by V. And P, now our N, we know is 6.185 moles. Our R is always 0.08206 liters, atmospheres, moles, Kelvin. Our temperature is given to us, 298 Kelvin. And the whole thing needs to be divided by the volume of the tank, which is 12.5 liters. And so we plug that into our calculator and multiply across the top, and we get by 12.5, we get 12.1, we'll call it, 12.1 atmospheres. So it makes sense that a tank would be pressurized, be more than 1 atmosphere pressure. So I like that value. So we got that here. 12.1 atmospheres, that's our P total. Now we can proceed to figuring out our P helium and our P oxygen. How do we do that? We need the mole fractions of each of those. Well, we have the total number of moles and we have the mole of each of them. So let's put over here our chi helium. Mole fraction of helium is just going to be 6.05, right? Moles helium divided by 6.185, 6.05 divided by 6.185, that equals 0.978. And so we can put that on our little list here. And we know our P helium is just equal to our chi helium times our total pressure. This is one way of defining what total pressure is. So that's 0.978 times our total pressure, which was 12.1 atmospheres. And so times 12.1, we get 11.8 atmospheres. So we can put that for down here. And right away, you can figure out what these are by subtraction. This better be 0.3, but let's go through it because the total pressure is 12.1. and there's nothing else than helium and oxygen in there. But our chi oxygen is 0.135 divided by, right, that was our number of moles of oxygen, divided by our total number of moles, 6.185. And if we divide that out, we should get something like 2.2, because our total mole fraction percent has to be equal to 1. And we do indeed get 2.2% or 0.022. So put that here. And again, we'll use the same relationship as before, but this time for oxygen, P oxygen equals chi oxygen times P total. So our last calculation for this video is P oxygen equals 0.022 right there, times our total pressure, which is 12.1 atmospheres. And if we plug that in, we get 0.3 atmospheres as we predicted. Again, this all makes sense because 11.8 plus 0.3 equals 12.1. So that's a calculation, calculating everything we could about all the mole fractions, the partial pressures of this mixture of gases.